Welcome everyone. This is Making Tools for Night in the Woods. My name is John Manning, and you can follow me on Twitter here. And I co-run a little studio called Secret Lab. I'm a game dev, because many of us here are. And I'm also an author. I've written a couple of books. A couple of them are on Unity. That is a shameless plug. I work on a game called Button Squid. It's a charming little puzzler that's coming out soon, I hope. Fingers crossed. And also a really fun game, really beautiful game about Leonardo da Vinci, the life and times of him. Cool. So one of the things that we did early last year was we worked with Infinite Fall and Finji of Canterbolt and Overland fame to get a game out called Night in the Woods. And Night in the Woods was fairly well received, if the awards that we got were any indication of that. Now, I'm not going to make any assumptions about whether people here have played Night in the Woods or not, so in case you haven't played it, just a quick background on it. You play May. She has just dropped out of college and has moved back into her family's house in Rust Belt, I want to say USA, but you know, we're a bit weird about that. And she finds that all of her friends have moved on with their lives, whereas she really hasn't. And it's a very narrative-heavy game. It's a lot of story focus. Also, I just freaking love the art in this. Scott Benson's a genius. So there's a lot of content in here that relies on two things. One is the extremely nice artwork, and also the extremely nice dialogue, of which we have lots of both. So, as you can probably guess, this was a game written in Unity. That's one of the main reasons I'm here at Unite. And today, I'm going to be talking about how we made the tools that we used to produce the game, also some more general advice on how to make good tools, and also how to make tools in a good way. So, we have a good set of things to talk about today. So, the first tool that I'm going to talk about is a tool we made called Yarn Spinner. Yarn Spinner came about as a solution to a problem that I think faces a lot of very small independent game dev teams. And that is that the team was very, very constrained. The total number of people who I think have touched the project is less than 15, and that includes publishers. So one of the problems was that Scott Benson, who I mentioned a moment ago, he's the main artist on the game, but he was also the lead dialogue writer, and that meant that he had no time to learn any other task. Now, in a lot of narrative-focused games, the way that we implement dialogue is typically with some kind of scripting language. I know that, for example, Double Fine uses a lot of Lua, and they do the implementation of the dialogue system in Lua. So you actually write a Lua program that is the script, as far as I understand it. Now, we actually applied a very similar technique to this in Night in the Woods, only we made it even easier for our non-programming artist/writer. So Scott spent most of his time in a cafe either drawing or writing dialogue. And when I say in a cafe writing, I mean on paper. So, for example, this is the design notes for the party scene that takes place in the latter third of the game. So lots and lots of direct writing onto paper, which would then get transcribed into into text files. We took a lot of inspiration from Twine. I'm curious here, who here has never heard of Twine? Wow, less than 10 people. Okay, so Twine is an amazing tool for creating interactive text-based experiences. It is a tool for creating a combination node-based and script-based game for typically for HTML. Only you can also produce non-HTML games in it as well. It makes it very, very easy to produce simple text-heavy games, as well as more complicated games that have a text focus. A lot of people's first ever games are written in Twine, and for good reason. Twine's fantastic. So we liked Twine so much that the main programmer of Night in the Woods, Alec Holoka, invented a very, very similar, very, very inspired version of this, designed specifically for the specific requirements of Night in the Woods. So there was Twine, and so we made Yarn. Yarn is a combination of a node-based scripting language, a node-based tool and a scripting language. So you can put scripts into nodes those nodes can connect to other nodes. And so you put, for example, one scene's worth of content into a node, and that node can contain a little bit of a program that describes what is said and who says it and what the stage directions are. So this is an example of, this is actually our demo project. This actually comes with what, if you download Yarn Spinner, which is the execution environment for Yarn, this is actually our demo project. This is almost all of it. So I'll be zooming in a little bit on some examples of Yarn script. This is a little more complicated. This is actually a screenshot of some of the code that was used to write Night in the Woods. This is actually most of the code used to run Laurie. If you've played Night in the Woods, Laurie is the mouse that you find in the middle of town on the first or second day. She's the extremely cool kid. And zooming in a little bit closer so you can actually read the code, we use this for some of our branching dialogue. So you can literally see the diamond shape that a lot of people talk about when they describe branching narratives, where you branch and you can choose one of two options, but then they merge back together and the player has some illusion of having influenced the game. So a lot of what you're seeing on screen here is largely just lines of dialogue, stuff that the player would see in the speech balloons, but can also be used for controlling the flow inside the script itself. And this is probably one of the best slides here that describes what Scott was doing, because as Scott was writing and Alec was transcribing, putting it into the scripts here, you can see what Scott wrote is almost literally what ends up in the script. We don't require any knowledge of programming. If you want to focus on making good lines of dialogue, you can just transcribe that in and then have your programmer come in later and add in the additional logic required. So for example, here's part of the conversation that May, the main character, can have with Laurie, where we actually do a check on a flag to see whether we can go on a certain adventure with the character. We have some really nice syntax as well. So for example, these arrows that are visible roughly halfway down the screen set up very, very lightweight choices. So rather than having to manually create a new node to go to let the player choose, we can very quickly and easily set up options for the player to choose from, and then run some text, and then go do something else. So what we find is that even when the player has no actual control over the gameplay with these choices, simply having choices presented is enough. And this is a thing that's been known to narrative designers for a long time. So one of the things also that we are also proud of is it was very, very easy to modify the grammar as needed. Very late in development, we realized that we needed to have localization for reasons that are going to be shipping soon. So we added in tags at the end of these lines. And so we have tools that will actually read and repass the content and generate, for example, the spreadsheets that are often typically used for localization. Everything you've seen so far is largely dialogue, but we can also use it to control more action-heavy scenes. So this is a scene that takes place fairly early in the game where May is at a party and has maybe a little bit too much to drink and embarrasses herself. And so there's lots going on in this scene. We have characters walking around. We have the player jumping up onto a stump to be embarrassing. And all of these purple highlighted items, all these things in between chevrons, they're commands. They're instructions to the engine to start doing actions in the scene. So Yarn was the language that was designed and was finalized about halfway through development. And then about roughly, I don't know when I arrived on the scene, but it was not too long after it was released. I found it and I made what I hoped was a better version of it, and that became Yarn Spinner, which I released as open source. It was liked so much by the development team that they actually brought me on, and so now I wear this t-shirt. So Yarn Spinner is a standalone .NET library. It actually has no dependencies on Unity at all. It just happens to have a couple of bindings that are optional. So I have seen, for example, some people using Godot using Yarn Spinner, which is really cool. I mentioned that it's open source, and I'm going to come back to it being open source because it's extremely cool to release tools like this as open source when they aren't part of your core business model. And even if when they are part of your core business model, maybe consider it as well. One of the reasons why it's a good thing is because it enables others to make modifications and contributions to your code. We have had a pile of awesome new things coming in. We have people rewriting the entire system. This is actually a merge pull request that came in a little while ago that actually rewrites the whole thing and makes it run on Electron, which is the platform for writing cross-platform GUI applications. So this is a huge amount of work, and they were just able to merge it in. And we love them for doing it. We've also seen some additional side projects come in as a result of being open source. Jacquard is one. It's a alternative editor for writing Yarn content. So I think there are some people in the room who are using Jacquard. Raise your hands if you are. Okay. All right. I made people outside. Oh, well. And also, Bondage is Jay Haley's implementation of Yarn in JavaScript, which is really cool. So if you're interested, lab.to/yarnspinner. That's actually a link to just our page on it. It's all really good and awesome. Okay, so that's the first tool that we made and released. The idea was simply just to see something that was already in use and try and find a way to improve it, and then release it as open source. I'll come back to open sourcing again later. Okay, so taking a bit of a breather for a second. That is part of the code that shipped in the first version of Night in the Woods. Now, what we're doing right now is we're bringing the game to iOS. Now, there are a couple of differences between, for example, a PlayStation 4 and an iPhone. Trust me. So one of those is memory constraint. The lowest end device that we support is a 1 GB device. Now, about 60% of the RAM on an iOS device is available to applications. The rest is reserved for iOS. And in fact, as you approach and exceed that threshold, iOS will actually terminate your process, which means that comparing that to, for example, a PS4, actually thinking about the PC requirements, the minimum RAM required on the PC version is 4 GB of RAM. So we have 600 megabytes of RAM, and we have to fit 4 GB of stuff in it. Cool. So, just to get technical on you, 4 GB of RAM is actually bigger than 1. So we needed a tool that would actually compress the large amount of sprites in the game into a smaller amount. And so I wrote a tool called Grabthar's Hammer, which produces significant savings. So, thank you. So, there are a few different ways that we already can apply these techniques to reduce memory. One of these is texture compression. So I'm guessing every game you've ever touched, both made and played, has made use of texture compression. There is varying support for the different kinds of texture formats available to you on mobile platforms inside Unity. So the main two are PVRTC and ASTC. PVRTC is older and a lot more supported, as far as I understand. Just about every single modern, certainly know that every single iOS device supports PVRTC, and most Android devices these days support PVRTC as well. The older ones tend to support ETC, which ASTC is more recent, much better, has better picture quality, and also better compression at the same time, but is really, on iOS devices, only available on the A8 chip and later. So we can't, there's actually no way to release an app onto the App Store and say, oh, and this only works on A8. So you have to support PVRTC if you want to have texture compression. At least you have to put that as part of your build. So texture compression is one method. And one problem with texture compression is it can significantly reduce the quality of your image, especially with PVRTC, especially if your sprites have lots of alpha content because of the way that PVRTC tends to work. You get fringing, you get blurriness, it's not amazing. So what are some other ways? Well, one of them is vector tracing. So Night in the Woods' style is very flat, lots of simple curves. And so vector tracing is the process of taking your bitmaps and figuring out what shapes are in the bitmaps. Now, you might be wondering, well, why don't you use the source assets? And the reason why is because they were all done in After Effects. So all of Night in the Woods was done in After Effects. There are ways to produce vectors from After Effects, but not in ways that can be easily translated into Unity. Because, for example, we made very heavy use of the puppet modifier in After Effects, and that actually creates a triangulation of the actual asset, which then gets deformed, and there's no easy way to replicate the exact same mesh in Unity because you don't know how the puppet's doing it. So it just became a lot easier just to generate all the sprites and then work with all the bitmaps. So next game we do, we're not going to do that. But yeah. Another problem with vector tracing is it does not preserve the small detail well. So we end up with like little weird bumps and nodules, especially at the corners and intersections of things, and we tend to require hand tuning for the best results. That's not really going to fly. We have over 4,000 individual sprites. I have better things to do with my time. So the other way we can do this is with texture atlasing. Again, most games that use sprites make use of texture atlasing. This is actually great for PVRTC compression. In fact, it's necessary because we have non-power of 2 non-square textures, and PVRTC requires both of those. Requires both power of 2 and square. Now, that's great, but it does tend to result in wasted space inside the atlas because you can't perfectly pack these non-square and certainly not rectangular images. For example, May is, she's got arms sticking out, she's got a head, she's got circles that won't fit. So we end up with a lot of empty wasted space that's resident on the GPU, taking up memory, and it's not great. The solution that we have hit upon and in active development is Sprite Dicing. Sprite Dicing is a technique in which you divide a sprite into multiple different pieces, you discard any piece that is fully transparent, and you pack the remaining into a smaller atlas. This results in better total usage of the atlas. You have much less area on the atlas that is fully transparent, which is therefore wasted. You're also able to remove any area that is transparent in the original sprite, and also, and I'll come back to this, not every piece of the original asset must be kept. Well, excuse me. So, this, for example, is one of our frames from May's run cycle, which that white area around the outside is actually part of the original asset. What we're doing is we're actually dicing it and then discarding any transparent area, packing it back into a much smaller image. So it's much more efficient. It's also power of 2. This is not a new technique. And the earliest that I was able to find was Chopper, which was one of the tools used for developing the Virgin Media 1993 game Aladdin. So Chopper was able to divide it up and pack it in a more efficient way for the platforms that it ran on, which was nice. So our process is basically, we take our original sprite, we first of all crop it to the smallest area, and you can see that red area that I've highlighted, that's wasted transparent space. We then divide it up into pieces and throw away any piece that is fully transparent. So you can see the amount of red area has now shrunk. What we then do on top of that is we then trim each one of those pieces, and now we have even less wasted space. We're left with a whole bunch of different small pieces, which we can then pack. So, to reconstitute the image, we generate a mesh which samples from that atlas and then run that in the game. Now you'll notice that we have a higher mesh density, which is not a great thing. So we don't get an ideal mesh out of this, but we do get a total net memory reduction. So as I mentioned, we get better atlas coverage. These atlas textures are further compressible using PVRTC if necessary. And also the shader required to do this is very, very simple. It's just an additional texture lookup. There are a few disadvantages. You do have to perform a pre-processing pass on all your sprites. There are limitations on the amount of, on the dimensions of your atlases. We have a high poly count, so there's padding, and also there's no built-in support in Unity. If there's anybody on the 2D team here who wants to talk to me about the adding support for UV coordinate configuration, come chat to me, please. Grabthar's hammer is a tool that I wrote in Python. It's actually external to Unity. And it just generates a collada file and the atlases. It uses some very, very cool Python libraries, so Pillow, NumPy, Scikit, some good stuff. And it generates the required assets used by the game. So one of the things that it can do as well is take advantage of redundancy inside the sprites themselves. So here's that same frame from May's run cycle. And if we zoom in on her shirt, we can see there's a lot of pieces here that are all the same thing. They don't all have to be they don't all have to be stored. We can just keep one. So this isn't just limited to flat colors as well. This is May's bed. She's asleep. We'll remove her from the scene. She's actually just a head and an arm in the scene. We'll get rid of the background and the glow. And so here's May's bed. And you'll notice that we have this repeated pattern. We can just keep one of those. So we're looking to find and remove redundancies from our assets. Now, there are two kinds of redundancies. There's spatial redundancy, and there's temporal redundancy. Spatial redundancy is when you have multiple copies of the same data in one image, whereas temporal redundancy is multiple copies over time, which really, in a frame-by-frame animation, means multiple copies across multiple images. So how do we find these? Well, first of all, let's look at how we find spatial redundancy. So spatial redundancy is actually quite easy to find. All you have to do is find pairs of chunks inside a single image that are the same. So again, here's that frame. Let's divide it up into pieces, and we'll pick a point to start from. Let's pick one in the middle of a face, and we'll compare the similarity between that green item that I've selected and all the stuff around it. And we record how similar each one is. And then we just keep moving. Notice we don't have to check the same thing twice, because comparing A and B will result in the same value as comparing B and A. So we can be quite efficient with this. Finding temporal redundancy is actually even more straightforward. So here's May's run cycle. Let's stop that and look at frame 1 and frame 2. Dice them up. We only need to compare the chunks in the same positions because we're already building the local spatial similarities in the single frame. So we don't have to worry about comparing all the different parts in frame 1 against all the parts in frame 2, because we're able to make use of the fact that we have this local analysis of the similarities in the single frame. The next step is to find clusters, so similar enough clusters. So imagine this is a simplified version that we have all of these pieces here, and I'm using color here to represent different image contents. We can apply an algorithm that was designed in the 70s called Tarzan's algorithm that is able to find locally connected, connected sets inside this graph here. So we're able to find any island of similar content. And given that all of these pieces are similar to each other, it follows that we can just keep one of them and discard the rest. So I've said similar a few times today, and it's worth considering what similar actually means. We can't simply compare the same pixels, because the human eye is a lot more forgiving of things being a bit different than actual computers. If we compare, for example, 2 blocks, then they won't be quite the same enough. Instead, what we use is an algorithm called structural similarity. Structural similarity is an algorithm that is able to tell you the similarity between the shapes in an image. It doesn't care about color, and it also is quite forgiving of noise, but it can be used to compare how similar, for example, 2 curves or 2 blocks or 2 shapes are in 2 images of the same size. Structural similarity is in fact used quite heavily in most video compression tools, and in fact, really, this is a video compression tool these days. So we compare all the shapes in all the pieces that we care about, and then we keep only the unique parts. We pack the atlas, and then we end up putting it into something like this. Now, you might notice that we have a bit of padding, like a bit of bleed around each part, and that's because of mip mapping. As our textures get displayed at smaller and smaller scales, to maintain a good quality image, we start mip mapping and going to smaller versions, and that tends to cause bleed in between the pieces. Because our pieces in the mesh are not continuous with each other, which they were in the original source asset, we end up with like weird grainy lines halfway through. It looks kind of bad. That's why our workaround is to just add padding around each chunk, which reduces the amount of usable atlas space, but it's, again, an acceptable trade-off. So padding is required, and to zoom in a little bit, you can see I've exaggerated the padding here. This is way more padding than we actually use, but it gives you an example of what's required here. We then can generate our mesh. So each chunk becomes a pair of triangles, because it's just a square, and we encode the texture coordinates. We actually make use of texture arrays. I'll mention that in a second here. So this is a picture of what May actually looks like in the game now. So this is actually a picture of one of the meshes of one of her frames. Now, I mentioned before that we have some limitations on atlas size. The maximum texture size available on an iOS device is 8192 pixels squared. Atlases must be squared, and we can't always fit every single chunk from an image or an image sequence into a single atlas. And also, we'll end up with wasted space as well. For example, here is May's entire run cycle. So her entire run cycle fits into an image which is 4096 squared, which is 16 million pixels total. But you might notice there's an empty space at the right and the bottom of the image. Again, we've been trying to minimize wasted space here. What we can do instead is, rather than using one texture, which is 4096, we can use 3 textures, which are 1024. And this significantly reduces the amount of wasted space, and everything's great. Problem: Now we have to work out how to refer to these 3 different textures rather than the single one that we had before, which was nice. So we use texture arrays. A texture array is a texture data object that can be uploaded to the GPU, which basically allows you to have multiple textures all of the same size stacked on top of each other, and you can refer to each texture by index, all from the same shader. And it's quite nice. You basically get to have multiple textures referred to by the UV2 channel in the object without having to worry about switching materials or worry about material property blocks, and it's nice. So we generate multiple atlases. We encode which atlas we're referring to in the UV2 channel of each vertex in the mesh, which does increase our memory load a little bit in the mesh, but as long as our our vertex count remains low, it's fine. And then in Unity, the characters end up using multiple sprite renderers because we keep the head and the body separate, for example, for flexibility. So we have written tools that swap the sprite renderers with mesh renderers, and then also update the animation clips to make use of these this new data rather than the original sprites. So what results do we get? Some good ones. So for example, here's our run cycle. You've seen it before. Here's the same image, and I'm going to, just before I hit the next slide button, you'll see red and green colors. Apologies to those who have trouble seeing that. And it'll also be flickering a little bit. So just FYI for anybody who's sensitive to that. But what you'll be seeing is green colors represent parts of the sequence that were reused from another frame. Red represents parts of the image that is unique and could not be deduplicated. So you can see the flat colors in the interior of her head and her shirt. There's lots and lots of redundancy that we can exploit. So we can get rid of that completely, and that just is not kept in the atlas. We don't need to store that in memory at all. The stuff around the outside is a lot more unique, and so we're forced to keep that, but fortunately those pieces are quite small. Now this is in fact one of our worst case ones. I'll show some numbers in a moment. Here's the same thing running at a slower frame rate so you can see a bit more of the detail. Okay, so how does this go? This is a sequence of 23 frames. The original source assets are 720 by 720, and they're stored with red, green, blue, and alpha channel. If we were to compress these with 4 bits per pixel PVRTC, then we would achieve 2.68 megabytes worth of data. That's actually being overly generous to PVRTC because we're assuming that PVRTC can handle non-power of 2 textures, which it actually can't. But if it did, then it'd be that. But following our technique, we actually get 1.5 megabytes. So that's 55% of the original. So we've almost halved it, which is great. But I mentioned this is actually one of our worst cases. This is the bed sleeping animation. So this is May pulling her blanket back, getting into bed. And you can already see there's only one moving part of this image. So if we look at this with our debugging view turned on, look at all that green. So the stuff that never moves stays green almost all the time. Each individual piece flashes red for the one frame that it's unique to. So every time you see a speckle of red, that's the one frame where that pixel actually came from. And really, only the moving things, the outside of the blanket, tends to be continuously red because that's the stuff that isn't reused across other frames. So here's the same thing running at a slower frame rate. And you can see how much we're able to reuse. Now in this case, this was 106 frames at 1024 by 512. Following the same settings, the original would be approximately 10 megabytes of data, but with our approach, it's actually 1.5, which is only 15% of the original, which is a significant savings. We've made some other smaller tools for Night in the Woods. So for example, I mentioned animation clips having to be modified. So we've written tools that will automatically walk the hierarchy of one of our characters and replace it with the new sprite system that we've developed. It'll also walk through all of the various pieces of our characters and analyze any other clip that makes reference to the sprite renders inside them. All the usual stuff as well, most of Unity has been replaced with our own code as far as the menu system goes for all of our builds. There's extremely heavy work on wizards and custom editors. So for example, here's part of Yarn Spinner that detects any errors. Don't be afraid of the Unity of the editor API, and use link. It's great, especially in the editor, where you don't have to worry too much about the about the garbage collector ruining your gameplay experience, because you can tolerate that a little bit. So, for example, here's some of our code that is used to find find any asset that is incorrectly tagged as unused. So, I'm running out of time, so I'm just going to skip through this quickly here. Try not to make a product as you're making tools. It's very easy to fall into the trap of making a thing for yourself and getting stuck on that. You're making a game, not a tool product. Resist the urge, because you're really busy. You don't need more support load. And if it's just your team working on it, you have more control over that. With one exception, and that is open source your work, because you should not be afraid to give your tools away. It helps other people. It can help you. It's very, very straightforward. Simply choose a license, write a README, adopt a code of conduct, and then tell everyone about it. That's what we did. You can find information on what license to choose at chooselicense.com. There's a great reference for code of conduct at contributorcovenant.org. It's not the only one, but it's a pretty good one. And also, opensource.guide provides a great resource for just how to do open source. All right, that's me. Hopefully you learned something. Please go and buy Night in the Woods. Cool. I don't think that we have time for questions. So if anyone wants to chat to me, I'll be outside. Cool. See you later.